we're back, and now let's go to the convergence rate of Tikhonov regularization, where we fine-tune the regularization parameter by discrepancy principle by Morozov with tau greater than 1. And now let's add this condition where if x dagger satisfies this abstract source condition, where x dagger is equal to this value of this term over here, that a star a raised to eta, or nu rather, times omega for some nu between 0 and 1/2, and omega is in this space over here, then there is a constant c depending on these parameters here, so that we have this error estimate there. Now, what this tells us is that for the discrepancy principle, our approximation error is of order delta raised to 2 nu over 1 plus 2 nu. And in regularization theory, you can check the reference that I mentioned. I also mentioned is that the book. This is actually what we call the order optimal convergence rate for selected values of nu. Okay. In particular, if nu equal to 1/2, then your convergence rate is of value, the noise level raised to 1/3. Am I right? Yeah. Oh no, it's actually 2 times. Oh, it's actually 1. It's not. Sorry, it's not 1/3. It's 1 plus 2. Oh, it should be 1/2. So that's 2 8. If you substitute, that's actually 1/2. Sorry about that. So that's 2 times 1. Yeah, that's really 1/2. And you can see that's also the best possible error. The best possible error that we can get for the Tikhonov regularization. So that's the square root of the noise level if eta is equal to 1/2. Okay, and then let's prove this one briefly. So let's consider the two cases based on the discrepancy principle. First, in the first case, let's say if the noisy data is dominated by the noise, then what this tell us from the previous discussion is that this means that the regularized solution must be equal to, rather alpha must be infinity, so that means x sub alpha delta, the regular solution must be 0, so that means you can just consider the norm of x dagger. Okay, and then by this condition over here, we can estimate the norm of y in terms of the noise, and by the condition on y delta, the norm of y must be bounded above by the noise times tau plus 1. And then by using the source condition on x dagger and the interpolation inequality, which is actually not quite like that. Let me correct that. If you remember from the interpolation inequality, you can review in the slides that the norm of a star a raised to r times x is less than or equal to the norm of a star a raised to q raised to r over q times the norm of x raised to 1 minus r over q, where q is greater than r. Oh, less than 0, yeah. Okay, so what we'll do is this, we can estimate this error over here, okay, which is equal to, let me just change the color. Oh, I actually have one here. Where the norm of alpha delta, I put some square there, so square, and then by inner products, that's just equal to this one. And then by applying the source condition, this is equal to, I can put it here, that one. That's A star A eta times omega times x dagger. And now note that in yesterday we know that A star A raised to B is a self-adjoint operator. So its adjoint is just itself. So therefore we can move this one on the other side, so that just omega times A star A raised to eta times x dagger. Okay. And then by Cauchy-Schwarz, we can bound this by the norm of omega times the norm of A star A raised to nu times x dagger. Okay. And that should be that one. And then by applying that interpolation inequality, where we let, as I mentioned there, if we let R equals nu and Q equals 1/2, okay? So of course we assume nu to be less than 1/2 here. So therefore by applying it here, using the inequality, it will be less than equal to the norm of omega times the norm of A star A raised to Q, which is 1/2 times omega, still x dagger, yeah, raised to R over Q, that's 2 raised nu, okay, times the norm of x dagger times 1 minus R over Q, or that's 1 minus 2 eta. Okay. Okay, and then note in this one, we can express that in terms of A. And that's by this following observation. Observe that the norm of A star A raised to 1/2 of, let's say, any point x, okay, that's x squared, and then by inner products, that's just equal to this one. From spectral calculus, same as what we did. So here, this is self-adjoint. So we can move this one on these sides. So we end up multiplying these two terms, or rather by composition of functions. That's just x times A star A raised to 1. Okay. And then we have an adjoint here. We can move it here. So we have AX times AX, and that's just the norm of AX squared. And that means this one here will just be equal to that expression over there. That's AX dagger raised to 2 raised to nu times of x dagger raised to 1 minus 2 nu. Okay? And then from here, by simplifying that one, by dividing both sides by this term in terms of the norm of x dagger, we can show the desired result. Okay, as we have seen earlier, so here you have this next estimate here. As I mentioned, if you divide both sides by 1 minus 2 eta, at least the pointer works. So if you divide both sides by 1 minus 2 eta here, okay, over here, then you will get the desired result, which is equal to this one over here. And then you raise both sides by 1 over 1 plus 2 eta, we will get the desired convergence rate. Okay. Now for the second case, the techniques are just the same. So if you consider the case that this one, okay, and then by minimality property, then we will get this one, okay? Okay, so we have this one here, same as what we did in the previous results. Now because in this case, alpha of delta is well defined by the discrepancy principle, so then this norm here is equal to tau times delta, and theta, tau is greater than 1, so it must be greater than or equal to delta. And then by simplifying the terms, then we get this result over here. Okay? And then consequently, we can manipulate that inequality to get the following. So if you want to get the following, so from that result over here, and we can manipulate it in a nice way. So that's, you can rewrite this one as this one. And then add both sides by that term on the left hand side, which is this one. So we have this one over here. Note this is non-zero anymore by the assumption, so we keep it there. There. Okay, and then by inner products, this left-hand side, or rather right-hand side, is just equal to 2 times the inner product of x dagger, and then x dagger minus x alpha delta delta. Okay, so I leave the details on you guys. You can show it in that way. Okay, and then again it works now by using the source condition on x dagger. You can again apply the same results by applying the same source condition. Then, of course, we can write this using the triangle inequality. Oh, not yet actually. So you can actually substitute x dagger here by this one. Eta times omega. Then again, same as in the previous case, that's just equal to omega times this one. messing up with the... And then we can apply the Cauchy wash. Okay, and then from that one, same as in the previous computation, by the same values of R and Q, we can get this one. Okay, this is very the same. And also again observing the previous result as well, that A star A raised to 1/2 of x, then you take the norm, that's just equal to the square of ax squared somewhere here. There. Okay. Then we can do the substitution again in terms of A. Oops. There. Can do again the substitution on A. Here, that should be new over there. I'll correct that one. And then by using the discrepancy principle over here, this though not yet actually, we can actually show that the norm of less than equal to the 2 omega times A times x two times nu, and then that's just equal to 2 times omega times, of course you can multiply A minus A times x dagger, but that's just equal to y. Okay, and then by applying the result on by triangle inequality, so what you do is just you minus y delta here plus y delta, then you will get this one times the norm of A x sub alpha delta delta minus y delta plus the norm of y delta minus y times 2 eta. Okay, yes. And then by note, this one is also bounded above by delta. From the discrepancy principle, because it's in terms of alpha of delta, that's just equal to tau times delta. Okay, and then if by actually manipulating that one, actually I have to correct that part over there. So this is equal to 2 times the norm of omega times that's tau delta plus delta, or simply tau plus 1 raised to 2 eta times delta raised to 2 times nu. Okay? And then from that we can actually that's actually 1, sorry. 1 plus 2 nu. Okay? And then by, of course, raising both sides by 1 over 2 plus, by raising both sides by 1 over 2 plus nu, so that will be equal to this one. Be less than equal to, so everything on the first terms here, everything that raised to 1 over 1 plus 2 nu times delta raised to 2 times nu over 1 plus 2 times nu. And this one will be your constant C. And that proves the result. And that proves the order optimality of the Tikhonov regularization. Okay. And then now, so now we have established the convergence and a convergence rate, it's time to show how do we actually do the implementation of the discrepancy principle. So first, in finding the parameter by the discrepancy principle, okay, we need to solve this nonlinear equation here, where so phi of alpha is equal to tau squared times delta squared, where phi of alpha is equal to the square of the residual in terms of alpha. And also recall that in our in solving the regularized solution for the Tikhonov functional, assuming it's invertible, then we get something like this one, alpha I plus A star A times inverse times A star times Y delta. And then, if you recall from spectral calculus, you can consider this one, okay? And then if you remember, if you let, in this case, if you let f of lambda be equal to alpha plus lambda times inverse, then we know that f of A star is equal to A star times f of A times A star. So therefore, we can rewrite this one in this way as A star. Actually, I think I wrote it. Yeah, I think I wrote it there. A star times alpha I plus A star times Y delta. Okay? Okay, and then by solving for phi of alpha, then it's easy to see that we can write A sub, oops, remember that. So therefore, from this one, we can write A sub x alpha delta minus Y delta equals this one, A times x alpha delta, so that's x sub alpha delta over here. Then we can, this one, so that's A times A star, that's inverse actually, minus Y delta. Okay, and then by then we can also rewrite this one in the following manner. So maybe I can write it here, or maybe I can just do it here. Okay, so from that one, on our expression for x of alpha delta, so we have A times x sub alpha delta minus Y delta equals A times A star times x sub alpha, oh, not yet, A star times alpha I plus A star inverse Y delta minus Y delta. Now, we can use the fact that identity is just equal to alpha I plus A star times the inverse of that exact operator. Okay? And then we can plug it in here. Use that one, and then that will be equal to this one. So that A times A star minus alpha I plus A star by just distributing it times alpha I plus A star inverse of Y delta. right? Okay, and then, so we put I over here actually, so that's actually something like that. Okay, and then simplifying this term over here, that's just minus alpha times that one. So therefore, P of alpha, which is just the square of the norm of A sub x alpha minus delta, square is just alpha squared times the norm of this one. Okay, and then also by a simple substitution, which I'll just outline. So if we let psi of t be equal to phi of 1 over t, then by substituting alpha equals 1 over t, then we can get this one. We can simplify it further. Okay, and then and from that one, that's I plus t, a star. And then by definition of inner product and the fact that this one, because it's A times A star, which is self-adjoint, this is also self-adjoint. Here, I plus A star inverse is also self-adjoint. So we have this one. There, okay? And then by using facts from spectral calculus, if you look at that last, if you look at this inner product over there, in particular in this first term here, okay, and we can actually show also that this is self-adjoint. And then from spectral calculus, this is equal to some terms which is like the sum of polynomials in terms of 1 plus t times sigma n squared raised to minus 2 and so on. Okay, so that's, I think there'll be some. We'll not use some We'll not do some spectral calculus now. We don't need it for now. Okay, and then, so essentially, if you take the derivative of psi with respect to t, it's simply like, so times some terms here, which I will not write anymore. So that means if you compute the derivative times, the derivative of phi is just equal to the term by term derivative of this one. It's in terms of t. Note from spectral calculus, which also you can check the reference of Engel, Hanke, and Neubauer, that book over here. This is just equal to some terms which you don't really have to worry because this one is independent of t. So you just need to compute the derivative of that one. So that's minus 2. So phi prime of t is equal to some sums where you have something like minus 2 times 1 plus t times sigma n squared times minus 3 times t. And that will be equal to, translating it to another inner product again, so that will be equal to minus 2 times. So the thing here is that you take note of sigma n squared takes the place of a times a star. So that when you translate it to operators, that's I plus a times a star times 2 minus 3 times that should be sigma n squared. Sorry. Sigma n squared, so that will be a times a star of y delta and y delta. You have a negative there, so that's less than 0. And similarly, you can compute the third derivative, and it will lead to a positive result, which means that the residual function in terms of phi is strictly decreasing, and at the same time it's a convex function from 0 to infinity. So therefore, for a sufficiently small initial guess T sub O, we can apply Newton's method, which is equal to this one. Okay? So it's T sub k plus 1 equals T sub k minus the function to be minimized here. So that's psi of T sub k minus delta tau square times delta square. Because note, in solving the parameter there, we need to find alpha, which is alpha delta, such that it's 0 of phi of t minus tau square delta square is 0. Okay? And then, of course, from the result on the convergence of Newton's method, then we have this equation over here, or the iterative equation rather, and this converges monotonically to T star, satisfying where T star satisfies the discrepancy principle with locally quadratic convergence speeds. And we use this Newton's method so that we can have an efficient way to compute the parameter alpha by discrepancy principle. And then we can translate this back in terms of alpha. So if it set alpha, k equals 1 over t sub k, and noting the fact that phi prime of t is equal to minus 1 over t squared times phi prime of 1 over t, then by variable substitution over here, we can get this one. Okay? And we will use this as our operator equation. And therefore, this iterative equation converges to alpha star, and it satisfies the phi of alpha star equals phi of alpha star equals 0. That should be phi of alpha. I think that doesn't work. Phi of alpha square equals also tau square delta square. Okay? And then from that one, okay, and that depends on and here, so therefore if we use this iterative equation, we need to start with a large initial guess. Okay? We cannot start with a very small initial guess, something close to 0, because the convergence might slow. So we start with the large initial guess, which is alpha sub 0, and this is the pseudo algorithm for applying discrepancy principle. Now let's try to go over this one. So here, suppose we have A, and note we need two things. We need the noise C data and the noise level, and we pick some tau greater than 1. Then we choose an initial guess alpha greater than 0. We set epsilon equals 1, which is for controlling the tolerance, and we start the iteration counter n equals 0. And then while the iterates are not close enough, that means while epsilon is greater than 10 to the minus 8, we do the following. First, we compute z, which is actually this one. That's actually z. And then after that, we compute x, which is just passing it to a star. Okay? X equals a star z. Note a star z has an important role here, because that's actually our it's actually not there. Okay. Note x here is actually our regularized solution. Okay, but note in the next steps we only need z in computing the next in the next candidate regularization parameter. So x is our regularized solution. It's also there, the one in the box. Okay? If you can see it there, and then After that, we solve for phi of alpha squared. So in steps 3 to 5, we actually implement this iterative equation here. Okay. Now, how does that work? Phi is equal to alpha squared times norm of z squared. Note z depends on alpha, so we need to compute the derivative appropriately. So, oops. Okay, so we need to compute the derivative appropriately. So if phi of alpha is equal to alpha squared times the norm of alpha I plus a star inverse y delta square, then by chain rule, it's easy. Note this is z. Okay. Then phi prime of alpha is just 2 alpha times the norm of z square plus alpha times the derivative of this one. Let's say d of t sub alpha of the norm of now, in the same way, note that this one here y delta square is actually equal to the summation of some continuous function in terms of f of sigma n square, then square, times terms of, I'll just write it. This one is just a spectral family of y delta, which some spectral family, but you don't need to worry about this term. You can check this notation from Engel's book in its first few chapters on spectral calculus. But don't worry about this one because this is independent of alpha. Now, in this case, f of lambda over there is equal to, what's it equal to? That is equal to lambda or alpha times lambda plus, that should be sigma n square. Okay, yeah, in this case, let me check that one. It's somewhere, it's just there. So that's just equal to f of, what should I use? Maybe I'll use alpha or lambda. Oh, actually, I'll have to use alpha. You have to use alpha over here. Okay, and then you have that one. So again, sigma n squared corresponds to 8 times a star. Okay, and then f of sigma n squared, f of sigma n of lambda. I'll just have arbitrary lambda, and f of lambda can be equal to lambda plus sigma n squared to the minus 2. Okay? And so that's the one opposite. I should use alpha. Okay? And then if you take the derivative of this one, so d over the alpha of that term over there will just be equal to summation of some terms which has contains something like minus 2 alpha plus sigma n squared to the minus 3. Okay? And then if we translate that further, let me just. Okay. So there's some terms there, and then, oops. No. Okay. So what happens is that if you have inverse then y delta square, it will just be equal to the summations of some terms which has minus 2 times alpha plus sigma n square to the minus 3, okay, times d sub a lambda of y delta, something like that. But if we pattern it in terms of this one, this will just be equal to minus 2 times, we can now apply alpha times I plus a, not sigma, is sigma n squares on a star, y delta, and then y delta. And this gives us a very compact way of computing in the algorithm, because as usual, this is self-adjoint, so we can also the multiples of the factors of this one, so we can write it as in this way. Times minus 2. You can put the minus 2 here. And then for the minus 1, raised to the minus 1, we can put it back in the other pair on the inner product. Okay? Okay. And note, this is just equal to z from the algorithm. Okay? And also, this is just equal to minus 2 times alpha I plus a star. Then we can write it in terms of minus 1 and then times the same term, inverse of y delta, which is just z and z. Okay? And then that leads us to the term on line 4. That's why you have minus 2 times alpha square. Okay, this minus 2 times alpha square times that inner product over there. And then update alpha 1 using the iterative equation. And then check the epsilon. And then we terminate once the alphas are close enough. And this outputs n the number of Newton iterations. And note x is our approximate solution. So this is a quite, so far, pretty efficient algorithm. But note this requires solving for z. And note the intensive part here is actually the one here where, because you need to invert this matrix so that numerically that means you have to solve a linear system in step 1. Also in step 4, we'll also need to solve a linear system here. Okay? And then with inner products, and then that's it. Okay? But note, this is for linear problems as long as we know that we can invert the matrix stably. So here's how it works for some examples in the previous one. So here's an example. Suppose if you have tau is equal to 4, we had 11 iterations, so we have this reconstruction here. If you let tau closer to 1, let's say 2, then note it will take more iterations than the one where we use a larger 4, and then this is our regularization parameter. So it gets small. And if we use a smaller tau, which is 1.5, then we get not much of the same, well, not much, not so different here. But notice here, if tau is 1.05, notice this is the regular solution. Notice it reconstructs the non-smooth solution here. Okay, and then of course, as you notice, that it's still not, it doesn't really cap. We can do much better by maybe using tau over here, but I think this is probably the nicest solution we can get. But we can actually use a smaller tau, and that will mean the more iterations. But by discrepancy principle, we know that this is already the best reconstruction that we can get. Note, tau is something that we set beforehand before using the discrepancy principle. I mean, in applications, you can always fine-tune it. Oh no, you don't have to fine-tune it. You have to fix it at every scheme of this regularization method. Okay. So that's something about for the non-smooth solution. And here's another one. But here, notice we have this reconstruction under different noise levels, delta and alpha is by discrepancy principle, and across we use tau equals 1.01. And notice that from left to right, we use from down to bottom, top to bottom, we use the delta that is slowly decaying to 0. And notice that as delta gets close to 0 like this, notice that the reconstruction gets better. As like here, notice this, it doesn't reconstruct well here and here. But notice we only use tau equals 1.1 over here. So normally, if you look at the smooth solution, notice that the Tikhonov regularization actually does better with the smooth solution. I mean, in the scheme, compared to the previous one where we have a non-smooth solution, notice the reconstruction is not so perfect, which is what we would expect in a Tikhonov regularization. In regularization in particular, okay? Because in the first place, we have data that contains with noise. And then, as you notice, we have a variational regularization that requires solving a linear system at every candidate regularization parameter alpha. In some applications, especially when you deal with a very large problem in terms of number of variables and equations, we know that solving a linear system can take actually a lot of computational effort. What we will describe next is an iterative scheme for solving the linear inverse problem with noise data. And that's something actually related to least squares, and that's based on the gradient scheme that minimizes this least squares functional. Note, because if we start with a linear inverse problem, ax equals y with the noisy data, of course it's ill-posed. Because it's ill-posed, solving this least squares minimization, which is minimizing this functional here based on the least squares, it's also ill-posed. Okay, later on, so we need to do something about it. But using the gradient of this objective function, which is equal to this one, then this will lead us to the gradient method in finding the minimizer of this least squares functional. And that leads us to this iterative equation over here. And eta is some number that we choose, and we start at the initial guess equal to 0. And this method is called the Landweber iteration. And we will discuss that one next time. So again, the lecture slides are, if you missed it, it's on the chat box. And if you have problems with how to access the the slides. Do let me know. Do give me an email here. Okay. Where's my email? Yeah, it's somewhere far in the slides. You can find it in the slides in the first page. Okay. And if you have no more questions, okay, then yeah, I'll see you next time.